curve in calculus. And so with area under the curve, we very often get a little confused because we look at the data that we're given and we're saying, well, we have this graph, right? For instance, the first example. And we say the car travels at 60 miles per hour and it travels for 6 hours. Now, most of us can rattle that off fairly quickly. 360 miles is how far you would go. So what we do is we often use graphs of area to model velocity, distance velocity kind of problems, okay, by saying that the rate is like our derivative, right? So the rate is in miles per hour and the time is an hour. But if we find the area under the curve, we can come up with the distance. And so if you look at the first one where we have this area, a car travels 60 miles per hour, and let's say it goes for 6 hours, right? So if you look at the function y is equal to 60, it travels at a constant rate of change, so that would be the horizontal line, right? So each hour you drive 60 miles, right? And you could look at this and you could say, well, how far in 1 hour? It would be 60 miles, right? And how far in 6 hours? It would be 360 miles to get the whole area. So the area models 360 miles, which is 60 miles per hour times 6 hours, as you see in that last, right here. So what we're looking at here are rectangular approximations, and we're looking at left rectangular approximations and right rectangular approximations, which we talked about briefly, okay? Now, I'm using the notes. I got to go over them pretty quickly because I only have so much time to present this. So we've got, these are the notes from today. So we have the left rectangular approximation. You can see that if we had n is equal to 2, that means 2 rectangles. We get an approximation, which is an under approximation, but nonetheless, we get 7, okay, 7 units. And then for the second one, where we increase the number from 2 rectangles to 4 rectangles, which approximates the area under the curve, we get 8.75 for the area for those 4 rectangles when you add them up. Now, notice that for the first one, the delta x is the end of the interval minus the beginning over n, the number of rectangles. And that gives us our delta x, which we typically use b minus a over n. So it's going to be 3 minus 1 over n for all of these, right? So delta x is equal to 2 over n. And the first one, delta x is equal to 1 because it's 2 over 2. N is 2. The second one, it's going to be 2 over 4. Or 1/2. So each of the delta x is going to be equal to 1/2. So the base of each of those rectangles, 1/2. The height will be 2, 3.25, 5, 7.25, which is governed by the function x squared plus 1. So we will put the x values for the height of the rectangle, 1, square it, and add 1, we get 2. 1.5, square it, we get 2.25, plus 1, we get 3.25, and so on, until we get our 4 y values. Then we use the y values times the delta x, which is 1/2, which what we can do is we can add up all the y values, 2 plus 3.25 plus 5 plus 7.25, as we did in class today, and then take that sum and then multiply by 1/2, we get 8.75. And then I have the delta x is equal to 3 minus 1 over 6 subintervals to approximate the area. Notice that all of these are using the left-hand endpoints here. So the left-hand side of the interval for the first rectangle, second rectangle, okay? So the left-hand side will take you up to the curve, and you plot that point on the left-hand side of the rectangle to give you the height of the rectangle. So on the last one, using the left-hand side, we've got delta x is equal to 1/3, so we just continue to add thirds. And if your fractions aren't tight, you can think of it like this. 1 is 3/3. So add a third, you get 4/3, 5/3, 6/3, 7/3, 8/3, 9/3, which is 3. Okay, it makes it easier that way. So then we're going to input those into the function f of x, x squared plus 1, and we would get the corresponding y values that you see on the points above. Okay, then I add them all up, multiply by 1/3, because the delta x is the same. We can extract that 1/3 with the distributive property, and we get the area is equal to 9.37. Okay? So now those are all underestimates. We assume that the actual area is going to be a little bit more. Okay? Then for the right-hand approximation, the right rectangular approximation method, we're going to use the right-hand side of the rectangle. So on the interval, I'm sorry, from 1 to 2, then we're going to use 1 and get that height of 5. 3 is the right-hand side of the second interval going from 2 to 3, and then we have the height of 10. So when you see that, you've got 5 plus 10. The area sum is going to be 15. Now, these are overestimates. As you can clearly see, you have some stuff that's outside above the curve if you will. Then we've got the second one where we have n is equal to 4. Still, delta x is the one above. Delta x is still 1/2, but we're using the right-hand side of the rectangle. So you can see the heights then are 3.255, 7.25, and 10 using the function, using the x values 1, 1.5, 2. I'm sorry, I said that wrong. 1.5, 2, 2.5, and 3. We're not using 1 to get those points that you see. Okay, let me use a red here and put one more point here. Okay, so we've got those 4 points that will designate the height of each of those 4 rectangles. And we add them up, add up the y values, multiply by 0.5. Again, you could distribute, you could multiply each one of those heights by 0.5 if you wanted to, but it's just a little quicker when you know that delta x is the same for each one of your rectangles. And then I have the last one. Remember, you have to be a little careful when you have fractions. So again, we're using the right-hand side. Again, an overestimate. You would add up the heights of the rectangles as you see here, and then you multiply by the 1/3 in the end, and then you get 325 over 27, I guess, and the area turns out to be 12.037. So it goes, I don't know about that last one. Yeah, I guess that's right. So it goes from 15 to 12.75. It's getting smaller and smaller because it's approaching the actual value from an overestimate. Okay, now the actual value you can put into your calculator. You can do a math 9, and then you can put it in with the integral. You put in the 1 to 3 because you're taking the integral from 1 to 3 of x squared plus 1 dx. And enter that and you get 10.6. You should get 10.6 and it'll go out, ... Put it, okay. And now if you look at this though, if you took the last approximation where we said delta x was 1/3, and for the overestimate and added the underestimate together, and then divided by 2, you get 10.2723. So that to me, when you get that far where you add them, you get a pretty close estimate of what the actual value would be for the actual area under the curve of f of x. Okay. When we say under the curve, by the way, it means under the curve or actually it means between the curve and the x-axis. Okay. All right. Then we have the midpoint. So